it's just a possible formulation which proved to work well. Okay, so let's take it. An interesting question is what is the shape of this function? If we want to draw a graph of it, what is the shape? So in order to draw it, we have to draw over a graph f c star in the ordinates and c star in the abscissa. C star is varying from 0 to C max. So let's say that we already proved that the function starts from the origin and ends up at the point with coordinate C max and 1. So the question is, what is the shape of the function in between 0 and C max? Okay, let's say that if beta k is equal to 1, the relationship reduces to this form. F C star is equal to 1 minus 1 plus C star divided C max. And therefore we can eliminate the two ones. You see that the relationship is just linear. This is beta equal 1. Beta k, sorry. Okay, what happens if beta k tends to 0? It's interesting. You see that the shape of this relationship is dictated by beta k. Beta k is the only thing that is the only parameter that is introduced here. So beta k is a constant, but if we vary this constant, the shape changes. And it's the only thing that we can vary here. The other thing are, okay, also C max we can vary it, but it doesn't have any effect on the shape in between. C max only determines the ending point of the relationship. And C star, it's a variable, and therefore it's not a constant. So, what happens again if beta k tends to 0? What happens if beta k is equal to 0? If beta k is equal to 0, whatever is the value between round parentheses, whatever value elevated to 0 means that it's 1. And therefore, we get f c star is equal to 1 minus 1 equals 0. So f c star is identically equal to 0. So what happens is that we get this kind of behavior, and then here we abruptly go to C max 1. Keep in mind that this is a limiting behavior for beta k equal to 0, and in general we don't have this, we don't get for a model this limiting behavior. But basically what it means, it's you may get it if the catchment is completely impervious. And completely impervious, let me think if I'm saying it correctly, because basically it means that for whatever value of C star, you have the storage in the catchment that is lower or equal than C star is 0. No, it's the opposite. It means that the catchment is everywhere. Let me think about it, because this is tricky. So this is the fraction of the area of the catchment that is lower where the storage is lower or equal than C star. So if the fraction is 0, it means that everywhere is higher, which means that the storage is everywhere equal to C max. So basically, if you increase C star, the fraction of the catchment where the storage is lower or equal than C star, it's always 0, which means that it's always higher until you get to C star, to C max, where you get the whole area of the catchment where the storage is equal than C max. And therefore, this kind of behavior for beta k tending to 0, you get it if the storage in the catchment is identically distributed and everywhere it's C max. Okay, what happens now if beta k cannot be negative by definition. What happens if beta k tends to infinity? So we analyzed 0, 1, let's try to increase it. What happens? Okay, what does it mean beta k equal to infinity? Basically, it means that, look at the content, what is inside the round parentheses, by keeping into account that C star is always lower or equal than C max. So this is generally lower than 1 or limiting behavior equal to 1. If this is lower than 1, 1 minus something that is lower than 1, the result is lower than 1. It's between 0 and 1. If you take something that is lower than 1 and you elevate it to the power of infinity, it goes to 0. So for beta k tending to infinity, fc star tends to 0, to 1, sorry. So you have something like this. And this is beta k tending to infinity. What does this mean? It means that whatever is the value of C star, whatever is the value of your storage, the fraction of the catchment with lower or equal storage is always equal to 1, which means that storage is everywhere 0. And therefore also C max should be 0. So the catchment is completely impervious, 0 storage. So as you see, I think this is indeed a very nice idea, because by varying beta k and C max, we can take into account spatial variability of storage in the catchment, which means spatial variability of surface runoff formation, without locating the areas where the catchment is indeed characterized by a certain storage. We don't need to locate these areas. This analytical relationship tells us the extension of these areas, which is what suffices to compute the river flow, without requiring this impossible detail to define of specifying where the areas are. by conveniently varying beta k, we can represent spatial variability from the limiting condition of spatial variability neglected because the catchment is everywhere impervious or everywhere characterized by a fixed value of storage. From this limiting condition, by varying beta k, we can describe several modalities of spatial variability. So the idea is indeed nice. Of course, we need to estimate Cmax and beta k. But potentially the idea is nice. You see that it requires some understanding of technical details, and it's not finished. We still have some technical details that are not really easy to get. Let's move forward. Okay, and then the next question is, provided that we indeed can fix the values of Cmax and beta k, we get a given shape of this diagram. Let's assume a specific shape that I'm drawing on the blackboard now. Okay, let's assume that it's like this. So this is C star, and this is, F C star, and this is C star. And this is Cmax. And this is 1. And this is 0. So let's assume that our shape is something like this. Which means that beta k is higher than 1, lower than infinity. Okay, now the next question is, let's suppose that over this catchment it starts raining. What happens? And how can I compute the river flow? And as a consequence, what is infiltrated? The storage. Because it's clear that over a catchment like this, if it starts raining and you assume that the catchment is dry at the beginning, what happens is that after a certain time, let's say 1 hour, 1 day, you get part of the rain that flows over the ground and contributes to river flow, because it falls over areas where the storage is lower than what rained. And you have part of the rain that infiltrates and contributes to an overall storage of the catchment. So if you look at the catchment like a tank, once again, you have storage into the catchment, which is given by infiltrated water. It infiltrates with different dynamics from here to there to up there. But anyway, if you look at the catchment as a whole, you get overall storage, which is given by infiltration. So after 1 hour, after the start of the rain, you get some water that is infiltrated and gives to you a storage, and some water that fell over areas where storage is less than rain, potential storage, and therefore contributes to river flow. Perfect. But what happens meanwhile? Meanwhile, while it rains, it happens that the areas that were at the beginning of the storm not saturated because they had a storage that is higher of the initial rain, after some rain, these areas store water and they may reach the limit of their potential storage, and therefore these areas get saturated. So the next rain, next hour, next day, while yesterday fell over areas that were still capable of getting infiltration, in the next hour, next day, this area may be saturated and they turn to areas producing surface runoff. Our task is to describe this dynamic process. I told you before, it's a dynamic process. So I have to take into account what is the storage into the catchment as time goes. So, in order to do that, I need to introduce a variable which is dynamic storage, which is CT. You see, it's depending on time. So it's no more C star, it's something that depends on time. And I introduced the dependence on time just to mean that my C star, I need to consider several values of C star as time passes. Okay, how can we define then CT? Let's define it in this way. CT is storage in the areas that are not saturated, that are not yet saturated. So let's suppose that you look to a specific location of the catchment. You can represent this specific location as a small tank with a storage C star. And let's suppose that this area is not yet saturated. Therefore, you have a storage here, which is CT. It starts raining. You have CT that increases because it starts raining. Let's assume that the area is not yet saturated. And then we indicate with CT this storage. And in order to fully understand what is CT, I can tell you that if you neglect any form of evapotranspiration, CT is nothing else than the rainfall depth from the beginning of the event. It starts raining. You indicate rain with PT, and PT is the cumulative rain from the beginning of the event. Basically, what happens in an area that is not saturated, that all the rainfall is infiltrated and contributes to the storage in that area, which is CT. CT is equivalent to the rainfall from the beginning of the event. Of course, if you get to saturation, this is no more valid, meaning that if you get to saturation, CT doesn't increase anymore because it's an upper limit. Saturation is an upper limit to the storage and therefore doesn't increase anymore, and you cannot say anymore that CT is equal to rainfall, because if it continues to rain, CT doesn't increase. And also keep into account that I am neglecting evapotranspiration, because evapotranspiration would decrease the storage. So I cannot say that CT is equal to PT. I can just say that it's equal to PT if the water column is not saturated and evapotranspiration is neglected. So I need two variables, but I can safely say that under these assumptions, CT is rainfall from the beginning of the event. Again, I define CT as the storage in the locations that are not yet saturated. Keep in mind that these locations don't produce surface runoff. They only produce storage, and therefore, if it rains over here, the effect of rain is increasing the storage, not producing runoff. The runoff is produced only when the area gets saturated. Okay, but still I have to answer the question. Given this situation, how can I compute surface runoff and storage? Okay, then I have a graph that helps me, which is this one. And in order to understand it, let's redraw it over the blackboard. And let's start from a value of C at a certain time t. So I'm placing myself not at the beginning of the rainfall event, because it would be too easy. I'm placing myself after a certain time, where it already rained Ct. Okay, so what happens here? It happens that I have a value of Fct, which I'm displaying here. And then let's suppose that after a time delta t, dt, I get more rain. And therefore I get to another value, which is Ct plus dt. And here I have another corresponding value, F C plus dt. So you see that there is a system that is dynamically varying. Time passes from t to t plus dt. During this time I get some rain, and as a consequence, as I can easily understand, the percentage of the catchment where I have a storage, potential storage, that is lower or equal than the given C increases. Look, what does it mean? Percentage of catchment where the potential storage is lower or equal than what it rained so far, because Ct is what it rained so far. What does it mean? That the percentage of area of the catchment where, again, potential storage is lower or equal than rainfall. This is nothing else than the percentage of the area of the catchment that is saturated. Because if you have a storage, potential storage that is lower or equal than rainfall, basically Fct is telling me what is the percentage of the area of the catchment that is saturated. So I start understanding that in this way I can compute how much is infiltration, how much is production of surface runoff, because I get an estimate of the percentage of saturated area as the rainfall event goes on. In particular, look, between during this time step dt, I have a rainfall that is falling, that is given by this difference. So, rainfall that is falling times the area of the catchment, which is along the vertical axis, because the vertical axis is giving to me percentage of area. If I mark this column here, this is the volume of rainfall. You see, if I multiply the rainfall I times 1, this is the volume of rainfall per unit area, but of course you know the area of the catchment. So this is the total volume. My question is, given this total volume of rainfall, what is infiltrated and what is transformed in river flow. You see the reply already here. But let's understand why. You see that there is a difference between what is below the beta K curve, the CT curve, or FCT curve, and what is above. So what's the difference between these two areas? First of all, take into account that dt is infinitesimal increment, and therefore, in this case, you see that FCT is varying between t and t plus dt. Actually, given that dt is tiny, very tiny, FCT can be assumed to be constant. You see here a change, but actually this is a very small time step, and therefore you can assume that CT is constant. So, what is, again, FCT? It's the percentage of the saturated area, and therefore, if I multiply rainfall times the percentage of the saturated area, and therefore I obtain this area here, I get what flows over the ground. I get the surface runoff. What remains above is by difference infiltrated. So this is why, from the beginning of the event, you can conclude that the volume below the curve, the red curve, which is the FC curve, is contribution to runoff. The area above the curve is contribution to storage. And you see that at the beginning you have a high contribution to storage and a low contribution to runoff because the catchment is not saturated. It's dry. As time goes on, you have the contribution to runoff that increases and the storage that gets lower and lower. Okay, there is an animated, everything is described extensively in the web page. There is also this animated figure where you can see the dynamical progress of the process. With this final part that we have to explain. The final part is what happens when you get to saturation and it continues eventually raining. What happens is that everything that rains is transformed in surface runoff. And this is why you get this rectangle here, which is surface runoff after saturation. So, provided that we understood, and I'm not sure if I explained well enough in order to make you understanding at this stage, but let's assume that I was good enough to explain. Provided that we understood, as I said, we now have to compute the surface runoff analytically. And therefore, you understand that what I need to do is to compute the area below the curve and the area above the curve as time passes. And therefore, what is the area below a curve? It's the integral. So I need to compute the integral of the FC depending over the extreme of integrations, the extremes of integration that I will decide. So let's compute this integral, and I need to rewrite the function f c, let's say fct, it's equal to 1 minus 1 minus ct divided by c max to the power of beta k. And let's suppose that I want to compute the storage into the catchment. So let's suppose that I want to compute the area above the curve, not the area below the curve. And if I indicate the storage with the usual, this is storage in the catchment, not storage in a specific location. Storage into the catchment. And this would be equal to Ct, which means rain from the beginning of the event, minus, let me give some more space here, because otherwise it becomes messy. Wt is equal to Ct minus the integral between 0 and Ct of Fct. And let me indicate it in this way. 1 minus 1 minus k divided by C max to the power of beta k in the key. Look at the variable of integration, which is varying between 0 and Ct. The variable of integration is Ct, but I indicated it with a different symbol as needed. Okay. So what is the problem here? Ct is given because Ct, it's rain from the beginning of the event. We are still assuming that we don't have any evapotranspiration, and we need to compute this integral here. So this is the complication. Okay. Okay, let's try to compute it. And on my web page you have all the steps, but don't look at here because it looks more complicated than it is. The nice feature of this function, and it was selected, this shape was selected because of this nice feature, is that it can be easily analytically integrated. So let's compute this integral, which is the integral here. So let's forget for now about w, and let's focus on the integral. We will come back to the computation of w later once the integral is computed. Okay. So this integral can be written in this way, like integral between 0 and Ct of 1 minus the integral between 0 and Ct of the second part, which is 1 minus k divided C max to the power of beta k in the key. So the integral here can be written in that way. And now, if I may, I delete the integral from which I started in order to make some room for the computation. Okay. This is equal to, I forgot here a D key, sorry. This is equal to key computed between 0 and Ct. First integral is very easy. Minus okay, now we have to compute the second integral. Let's compute it by intuition. Okay, by intuition it means that I try to understand how it looks. This is a function elevated to a power, And therefore, what I understand is that there must be the argument of the function that remains there to the power of beta k plus 1. And then I need to introduce a multiplier here, which is for sure beta k plus 1 at the denominator. And I have to take into account the fact that I have to compute the integral of the argument, the base of the exponential function, which is basically given by minus, so I have to change the sign here, C max. And this is to be computed between 0 and Ct. Given that we computed the integral by intuition, let's make a validation of what we guessed by computing the derivative. This is the derivative of an exponential function, which is equal to the exponent. It is like this. Let's compute the derivative. Beta k plus 1. The exponent, which multiplies C max divided by beta k plus 1. Okay, and then we have the base of the exponential function, 1 minus k divided C max to the power of beta times the derivative of 1 minus k divided C max, which is minus 1 divided C max. And therefore